Time travel. The very phrase sparks our imagination. It whispers of adventures in distant pasts and voyages to unknown futures. But what exactly is time travel? At its core, time travel is the concept of moving between different points in time. It's like flipping through the pages of a history book, but instead of just reading about the past or future, we get to experience it firsthand. Imagine walking with dinosaurs or joining a colony on Mars centuries from now. This idea has captured our collective imagination for centuries. The allure of time travel lies in its possibility of altering the past or glimpsing into the future. It invites us to ponder the mysteries of time and our place within its grand tapestry. While the reality of time travel remains a topic of debate, its hold on our fascination is undeniable. But is time travel truly possible, or is it destined to remain within the realm of science fiction? Let's delve into the science behind this captivating concept. The concept of time travel is deeply rooted in the theories of physics, particularly Einstein's theory of relativity. According to this theory, time is not a constant and unchanging entity. Instead, it can be warped and bent, much like space itself. This leads to the fascinating idea of wormholes, theoretical passages through space-time that could create shortcuts for long journeys across the universe. If such wormholes exist, they could potentially allow for travel between different points in time, not just space. Scientists and researchers have been exploring these possibilities for decades, trying to understand the fundamental nature of time and how it might be manipulated. However, time travel also brings with it a host of paradoxes and challenges. One of the most famous is the grandfather paradox, which questions what would happen if you traveled back in time and prevented your own grandfather from meeting your grandmother. Would you cease to exist? Some theories suggest that such actions could create alternate timelines or parallel universes, where different versions of events unfold. As we continue to advance our understanding of the universe, the dream of time travel remains a tantalizing possibility. Whether through the bending of space-time or the discovery of new physical laws, the quest to unlock the secrets of time continues to inspire and challenge us. So, while we may not yet have the means to journey through time, the exploration of this concept pushes the boundaries of our knowledge and fuels our imagination. The future of time travel, much like time itself, remains an open book, waiting to be written. To grasp the complexities of time travel, we must first venture into the mind of Albert Einstein, a visionary whose ideas have shaped modern physics. His groundbreaking theory of relativity revolutionized our understanding of space and time, challenging the very foundations of classical mechanics. Einstein's universe isn't static, it's a dynamic fabric where space and time are interwoven, constantly interacting with each other. Imagine a trampoline as a representation of space-time, a flexible and responsive surface. A heavy object, like a bowling ball, placed in the center creates a dip, distorting the surface around it. This is similar to how massive objects, such as planets and stars, warp space-time, creating curves and bends. This warping is what we perceive as gravity, the force that governs the motion of celestial bodies and keeps us anchored to the Earth. Furthermore, Einstein's theory proposes that time is not absolute. It is a variable that can stretch and compress. It's relative, meaning it can be affected by speed and gravity, altering our perception of past, present, and future. The faster you move through space, the slower time passes for you relative to someone stationary. This effect, known as time dilation, becomes more pronounced as you approach the speed of light. This phenomenon, known as time dilation, has been experimentally verified through precise measurements using atomic clocks on fast-moving aircraft and satellites. The implications for time travel are profound, suggesting that high-speed journeys could allow us to experience time differently, potentially leaping into the future while those left behind age at a normal rate. Imagine a spacecraft traveling close to the speed of light. For the astronauts aboard, time would slow down significantly compared to those on Earth. A journey that seems like a few years to them could equate to decades or even centuries passing on Earth. These concepts, while mind-bending, are grounded in the rigorous mathematics of theoretical physics, offering a glimpse into the possibilities that lie beyond our current technological capabilities. As we continue to explore the cosmos and push the boundaries of our understanding, the fabric of time and space remains one of the most intriguing frontiers, holding secrets that could one day unlock the mysteries of time travel. Time dilation, a direct consequence of Einstein's relativity, reveals the malleable nature of time. It demonstrates that time is not a rigid, unchanging constant, but rather a fluid entity influenced by speed and gravity. Consider astronauts aboard the International Space Station. They're orbiting Earth at incredible speeds. Due to their high velocity, time passes slightly slower for them compared to people on Earth. While this difference is minuscule, it highlights the reality of time dilation. But the effects of time dilation become even more pronounced at speeds approaching the speed of light. If we could travel at such speeds, time would slow down significantly for us relative to those on Earth. This concept forms the basis of the twin paradox. Section 4. Tunnels through space-time, the enigma of wormholes. Wormholes have long fascinated scientists and science fiction enthusiasts alike, offering a tantalizing glimpse into the mysteries of the universe. While time dilation offers a glimpse into the possibility of time travel, it presents a significant challenge: achieving speeds near the speed of light. The energy required to reach such velocities is astronomical, making it an impractical solution with our current technology. This is where the theoretical concept of wormholes comes into play. Wormholes, also known as Einstein-Rosen bridges, are solutions to the equations of general relativity that suggest the existence of shortcuts through space-time. Imagine folding a piece of paper in half. This simple analogy helps us visualize the complex idea of a wormhole. Now imagine a tiny tunnel connecting 2 points on the paper. This tunnel represents a wormhole, a hypothetical passage that could connect distant points in the universe. This tunnel represents a wormhole, a hypothetical shortcut through space-time. If such a structure exists, it could revolutionize our understanding of travel and communication across the cosmos. By traversing a wormhole, we could potentially bypass the vast distances of space and leap across time itself. This concept has been a staple in science fiction, inspiring countless stories and theories about interstellar travel. However, wormholes remain purely theoretical. Despite their intriguing possibilities, we have yet to find any empirical evidence of their existence. Their existence hasn't been confirmed, and even if they do exist, their stability and traversability by humans are uncertain. Theoretical models suggest that wormholes could be highly unstable, collapsing under the slightest disturbance. The very act of entering a wormhole could cause it to collapse, trapping travelers within its depths. This presents a significant risk, making the practical use of wormholes for travel a daunting challenge. Until we can better understand and perhaps even manipulate these enigmatic structures, wormholes will remain a captivating mystery of the universe. Section 5. The paradox of time: can we change the past? The tantalizing possibility of time travel inevitably leads us to a perplexing question. Can we change the past? This question gives rise to the infamous grandfather paradox. Imagine you travel back in time and meet your grandfather before your parent was born. Now, if you were to prevent your grandfather from meeting your grandmother, it would unravel your very existence. You wouldn't be born, so you couldn't travel back in time to change the past in the first place. The grandfather paradox highlights the potential for contradictions and paradoxes inherent in time travel. It challenges our understanding of cause and effect, forcing us to confront the mind-boggling implications of altering the past.